A 20 centimeter diameter, 2 kilogram solid disc is rotating at 200 RPM. So I'm just going to draw this. Okay, so it's rotating at 200 RPM, so that would be the angular velocity, 200 RPM. The units are not SI units, but it's still an angular velocity. A 20 centimeter diameter, okay, so this was a 20 centimeter diameter disc, so this is 20 centimeters. I'm just going to write omega initial here, so I have space above my drawing. Okay, so I have a 20 centimeter diameter, 1 kilogram circular loop, which is dropped straight down on the rotating disc. So I basically have a loop now. So it's the same size, except it's just a loop. There's a space in the center, okay? But it still looks like it's still in 3D, and it's dropped right on top of the solid disc. Okay, it's 1 kilogram, and the solid disc on the bottom is 2 kilograms. Friction causes the loop to accelerate until it is riding on the disc. What is the final angular velocity of the combined system in radians per second? Okay, so initially the disc and the loop above it are not touching. At the end, they're touching each other. So this is like a collision that's happening, but it's an angular collision. So things are rotating as they collide. So that's why we're going to look at angular momentum here, not just linear momentum. So for angular momentum, we know that it's conserved if there's no net torque acting on the system. And there's no external forces that are acting on the system. So since there's no external forces, then there can't be a net torque. So there's nothing externally that's causing these two things to rotate other than what's already happening in the system. Okay, so then we can say that the initial angular momentum, so L stands for angular momentum, is equal to the final angular momentum. Okay, and we're talking about of the whole system. So I'll put a little total here. L total initial is equal to L total final. Okay, so let's think about the angular momentum of everything. So initially we have a disk and a loop. So I'm going to write L disk initial plus L loop initial equals L disk plus L loop together. They're together. So they're going to be stuck together when we're done. So we're going to treat this like it's like an inelastic collision, but it's angular instead. Everything's rotating. So if we think about the formula for L, so remember if we had linear momentum, the formula was P is equal to mass times velocity. So P is linear momentum, mass for M, V is velocity. Now if we take that into angular momentum, the letter changes from P to L. Instead of mass, we have moment of inertia. Instead of velocity, we have angular velocity. So when we have a rigid body, this is the formula that we're going to use. The angular momentum is equal to the moment of inertia times its angular velocity. Okay, so let's use this formula here. So instead of angular momentum, I'm going to change it to I of the disk initially times omega of the disk initially plus I of the loop initially, omega of the loop initially, is equal to, now they're stuck together. So just like with linear momentum, when you have a collision and it's an inelastic collision and the two objects stick together, you would say, well, their velocity has to be equal because they're stuck together. They're acting as though they're just one object. Well, same with this system. They're stuck together. The loop is on top of the disk and they're now going to be moving together. So in that case, then the angular momentum, the moment of inertia would just be the total of the moment of inertias of each of the two objects. So just like we would have added the two masses, we're adding the two moment of inertias. So we have the moment of inertia of the disk plus the moment of inertia of the loop times omega final. Okay, so this should be very similar in your head to when we were doing inelastic collisions before, except I and omega would be replaced with M and V. Okay, so let's think about the formulas now. So the moment of inertia of a disk, you can look at the table. The moment of inertia of a disk is 1/2 mass of the disk r squared. I could put r of the disk, but the radius of the disk and the loop are the same. Okay, omega of the disk initially plus the moment of inertia of a loop is just m r squared. Okay, so that again is from the table. Omega loop initial is equal to the two moments of inertia put together. So 1/2 m dr squared plus m loop r squared times omega final. And the omega final, that is what we're looking for. Okay? They want everything in radians per second, so we need to make sure everything is converted. So this revolutions per minute needs to be converted. Okay, why don't we do that right now? So we have omega initial is equal to 200 revolutions per minute. I want to change those units to radians per second. So I'm going to get rid of revolutions first. Since it's in the numerator, I'm going to write revolutions in the denominator. Instead, I want radians. 1 revolution is 2 pi radians. Then I can convert my minutes, so I want to put minutes in the numerator, so it would cancel out with the minutes in the denominator. Instead, I want seconds. 1 minute is 60 seconds. So I can type all of this up on my calculator. And I get, I'm just going to leave it with a pi in it, 20 over 3 pi, so that it's more accurate. Okay, so now I have my omega initial in the correct units. So let's think about what we're going to plug in for everything. The mass of the disk, we know, is 2 kilograms. So this is my mass of my disk over here. The radius of the disk, well, it tells me that it's 20 centimeters. So then the radius of the disk is 10 centimeters. I need to change that into meters, so it'll be 0.1 meters. The omega of the disk, so the angular velocity of the disk initially, is what we just found. So this is my omega of the disk initially. Okay, then I have my mass of my loop, which is given to me. It tells me that it's 1 kilogram. The radius of the loop, well, the diameter of the loop is also 20 centimeters, so the radius of the loop is 10 centimeters, which is 0.1 meters. The omega of the loop. Okay, so initially, before the two objects collide, what is the omega, or the angular velocity of the loop? Well, it wasn't moving. The loop was just dropped straight down onto the rotating disk. It didn't have an angular velocity. So this is 0, which means this whole term goes away. Okay, then we have on the right side of the equals, 1/2 mass of the disk. Again, we know what that is, 2 kilograms. The radius of the disk, still 0.1. Mass of the loop is given, radius of the loop. This is radius of the loop in the disk, but they're both the same radius, so that's why I didn't really bother putting them in. And then we're solving for this omega final. Okay, so we're good to go. We just have to rearrange our formula. We have omega final is equal to 1/2 mass of the disk, radius of the disk squared, angular velocity of the disk initially, over 1/2 mass of the disk, radius of the disk squared, plus mass of the loop, radius of the loop squared. And now we can plug everything in. 1/2 mass of the disk, which is 2 kilograms, radius, which is 0.1 squared, omega, which was 20 over 3 pi, over 1/2 mass of the disk, radius of the disk squared, plus mass of the loop, radius of the loop squared. Okay, so type all this in with me as I'm typing it. Make sure that we're getting the same answers. And I get 10.47 radians per second. Okay, it's omega, angular velocity, everything was in SI units, so my answer is going to be in SI units. Let's look at the number of significant figures. We have 3, we have 3, we have 4, 3, 2. So our answer should just have 2. So I'm going to round that to 10 point radians per second. Okay, I put the decimal after the 10 to show that the 0 is actually significant. And that's it. So that's how you can find the angular velocity after a collision for an inelastic collision. All right, thanks for watching.